Assalamu alaikum students and welcome to another lecture of Slate. This is me, Khawaja Yasin. Let's study chemistry. So, when we talk about A-levels chemistry and especially the P4 chemistry, which is A2 chemistry, in the recent years, the topic of transition elements has now become the most important. If you go through the past papers, there are two or sometimes more than two questions comprising of this one particular chapter of inorganic chemistry, which is transition elements. Transition elements is something all of you have studied in your O-levels. That was basic. They are just there in between the periodic table. They don't follow the trends and they have a few properties. But in A-levels, we will talk about the fact that why do transition elements have those properties? Why do they have those particular chemical properties which make them distinct? But before jumping towards that, let's recall the AS. In the AS, so students, in the AS chemistry, you first talked about shells, subshells, and orbitals. Remember, a shell or energy level can further be divided, or it can be constituted of subshells. And subshells further have orbitals. In the case of subshells, we talked about four subshells: S, P, D, and F. Remember, for orbitals, each orbital can only have two electrons. So that is something fixed for orbitals. But now, again, talking about the subshells, we have S subshell, we have P subshell, we have D, we have F. In the AS, we talked about S and P. S can only comprise of a total of 2 electrons. D can have a maximum of 6 electrons. D can have a maximum of 10 electrons. And F can have a maximum of 14 electrons. And if one orbital can have only 2 electrons, so there will only be one S orbital. Only there is one S orbital. It's not the number of shells, it's just one S orbital. It will only have one S orbital. Talking about P, since there are 6 electrons, we will have 3 P orbitals. And when we talk about P orbitals, they were Px, Py, and Pz. This is a concept of AS chemistry. Now, jumping on to A-levels. Luckily, we will never be talking about F orbital. F orbital is a concept you won't be studying in A-levels. So let's ignore that. But talking about the D orbital. If it has 10 electrons, D subshell will have 5 orbitals. 5 orbitals, and they have their different names. And that is what transition elements are all about. So what are transition elements? Transition elements are D block elements. Now, what does D block means? That all the D block elements will have the valence subshell that will be a D subshell. Like, these are named depending on the valence subshell. Like, if you look at the periodic table, the first two groups, these are S block. Why? As the valence electrons are present in S orbital. If you remember the electronic configuration, you can easily decode that. Talking about these ones, is there. All of these, they are p block elements. Their outermost electrons are in the p subshell. But talking about these ones, these are the d block elements. They have their valence electrons in the d orbital. Outermost is the d. If we just talk about these ones, which again I told you it's not in your syllabus, these are lanthanides and actinides. These are F block. But again, not in the syllabus. So the reason we call transition elements d block elements is that their valence electrons are in the d1. And remember, only the valence electrons take part in bonding. So if they have their electrons in the d orbital, it's the d subshell that is going to be responsible for the chemical properties. And that is why they have different and distinct chemical properties in comparison to other blocks. So transition elements are d block elements. Now, as I said, a d subshell will have 5 orbitals. If you remember from AS, there's only one s orbital that has a spherical shape. Talking about the p ones, there were 3p. One p had a dumbbell shape. 2 balloons can be compared to that. That's a dumbbell shape. Whereas the dumbbells are the ones you lift in the gym, but you draw it in chemistry in this way. Now there were 3 p orbitals depending on the excess. If this can be called a z axis, x and y, the orbital if I make the orbital here on x-axis, that was 3px. If I make the same orbital on the y-axis, that was 3py, 2 lobes. Making it on z, that was 3pz. That is something I hope you recall about AS. Now talking about A2, 5 orbitals. There are different shapes, there are different names. So these are the 5 orbitals of d block. 5 d orbitals and their shapes. These are the 5 d orbitals and their shapes. If you notice that, this is the x-axis, this is the y-axis. There is one orbital called dx orbital, and it will only have 2 electrons as per the rule. Now, in this case, both will lie between x and y axis. Now you can see both the lobes are between x and y axis. Likewise, these yz, both are between y and z. In this case, in the case of p, they lied on the axis. In the case of d, they lie in between the axis for the first 3 ones. So dxy, when they lie between x and y, 2 lobes and lying between the x and y. Y and z, when they lie between y and z. Z and x, when 2 lobes, both of them lie between z and x. But there are 2 more. X square dash y square. What about that? One lies on x, one lies on y. So that is one shape. And the other one, zx square, both will lie on the z. I mean, it will just lie on the z axis and there will be a central lobe. You can either draw it this way as well. If this is one lobe, there is a ring, just a ring around it. That's z-axis. So students, these are the shapes of d orbitals, and they give them their very chemical properties. So transition elements have 4 important chemical properties, students. You have studied them in O levels as well, but there were 3 in your syllabus in O levels. So 4 chemical properties that the transition elements have. A, they have variable oxidation states. By oxidation states, we mean charges. So they can have variable charges, +2, +1, +3, +4, so on and so forth. B, they're used as catalysts. And this property is also because of the fact that they have variable oxidation states. You have studied it in physical chemistry as well, where you study the topic of catalysts, that how the transition elements, due to their variable oxidation states, can coexist in different ways. For instance, iron, +2, +3. So it can have both the states to make it stable as a catalyst. And it will revert back. We will discuss that when we are talking about this point. Third property, they form colored compounds. Now again, colored compounds. Color is because the light is absorbed and the rest of them are reflected. That is something you've studied in physics, the Planck constant. So that very idea will come in this topic of excitation or de-excitation of electrons between the orbitals, the d orbitals. As I said, these are d block elements. The properties that they have is only because of the d orbitals and d subshell. Last property, they form complex ions or compounds. So these are the 4 properties on which we're going to talk about in this chapter. Now moving on to the first property, which we will cover in this lecture. Variable oxidation state, which means they can have multiple oxidation states. If you recall it from O levels, iron had iron 2 +2 and iron +3. But let's simply discuss the first period. Starting off from Scandinavium, SCTI, then it would be vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So these are the first 10 elements. Now students, let's talk about their electronic configurations. You need to remember your concept from AS. If you do not, you can go on our YouTube channel and see the video where I have talked about the electronic configuration for in the AS tabs, not the O levels, please. That's a different topic now. So we need to know their atomic numbers, because atomic numbers mean electrons. So this is 21, 22, 23, 24, 25, 26. Let's make all together a full electronic configuration for scandium. So what are we going to do? Let's start from the first. 1s2, 2s2, 2p6. Remember, we have to accommodate 21 electrons. 2p6, 3s2, 3p6. Now, remember from AS that the energy of 4s is less than that of 3d, has lesser energy than 3d. And as per the off-bow principle, electrons are filled in the lower energy orbitals first. Although 4s is from the other energy level, but it has lesser energy. It is because of the shape and the other factors, but mainly because of the spherical shape. But 4s has a lesser energy than 3d, so 4s is filled first. So that is what we know, that in the case of d orbitals, it's the 4s. And secondly, till this point, we have talked about helium. It is argon till this point. Sorry, neon. Until this point, we're talking about argon. After argon, if you look at the periodic table, it is first calcium and potassium, and they are S block elements. So that further proves it that after this 3p6, we won't have 3d. We would rather have 4s2, which is for calcium and potassium, and then we are going to have 3d1. 4s comes first, then 3d. So the rule is we can ignore all of these and we can simply write argon. The noble gas is a checkpoint. So let's do it that way. 4s2, vanadium, 4s2, 3d2, 3d3, 3d4, let's keep on pasting it because it's going to be the same throughout. Only the number of electrons are going to change. So we know 3d5, 25, 26, 6, 7, 8, 9, 10. That is something we know about. If we make the electronic distribution with the boxes, we may be able to study more of its properties. But there is a special property, if you remember from AS, about the half filled, fully filled, and partially filled subshell. Fully filled means stability, half filled also means stability, partial is not stable. So, for instance, for S, full is 2 and half is 1. For P, full is 6, half is 3. For D, Full is 10, half is 5. So let's look at these. We have a different case for chromium and copper. They too behave differently here. Now, why does it happen so? Just look at manganese. It has a fully filled s orbital and half filled d orbital. That's stability. Perfect. When we look at vanadium, fully filled s orbital, but the outermost 3d is not completely filled. It's partially filled. It's neither half filled. This is half filled. 6, again, not half filled. That's partial. Partial. But something can happen in the case of chromium and later in the case of copper. I told you that how half filled and fully filled is something any element would want to stay in. If it's in half filled state, it's happy. If it's fully filled, obviously it's happy. But partially filled, elements try to ignore that state. So students, if we make the electronic configuration of chromium, this is the S4s2 orbital, 4s, and this is 3d orbital. So in the case of chromium, let me copy it for copper as well. Yeah. So in the case of chromium, we have 4s2, 1, 2, 3, 4. In the case of copper, we have now both of them have partially filled d orbital. But if one electron from the s orbital excites means going to a higher energy orbital. So this electron is removed and it comes here. So now we have half filled s and half filled d. Now both the orbitals are half filled. That is stability. So chromium prefers to stay in 4s1 and 3d 5 state. This is also stable. It can definitely exist in this state as well, but this is a better state. This is excited state. From AS, if you remember, this is ground state. This was ground state. This is ground state, and this is excited state. And it is more stable this way. Likewise, in the case of copper, this is fully filled, this is partially filled. Not accepted at all. But what if I excite the electron? I remove it from here, and the electron goes to this. And now it's fully filled. And that is how it becomes stable. So students, that gives stability. Now, coming to the concept of variable oxidation states. Two elements, scandium and zinc. The following do not have variable oxidation state. These ones do not have variable oxidation states. Zinc will only have +2 and this will only have +3. Now, there is a reversal of the conditions. I told you 4s is filled first and then 3d. But when we are removing the electrons, when electrons are removed, they are removed from 4s first. So when electrons are removed, they are removed from 4s first. So all of them will remove their first electron. First two electrons. That is why they have variable oxidation states. First, the s orbital loses its electrons, and then the 3d comes and plays its part. So if we have these so they will have variable oxidation states. Like how? 4s2, 3d1. Now, if I have to talk about the variable oxidation states that they would have, scandium, as I said, till 3s, it's argon. You cannot remove any electron. Now we only have 3 electrons at disposal. So this will only make Sc plus 3. It's fixed here. Now moving on to titanium. It has 1, 2, 3, 4 electrons. So if we remove 1 electron from 4s, that's plus 1, plus 2, plus 3, and plus 4. Because it can lose 4 electrons. Moving on. Plus 1, plus 2, 5 electrons. So we can go up till 5. Plus 4 is left. Chromium. Plus 1, plus 2, plus 3, plus 4, plus 5, plus 6. Manganese, highly important. Plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. So the numbers keep increasing. But after manganese, it keeps decreasing. Plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, then plus 5, then plus 3, then plus 4. Now, why does that happen? That we'll study in the topic of stability constant. But this is the reason they have variable oxidation states. And that is all for this video. In the next video, we'll talk about that why do they form complexes and why do they have colors. So thank you so much for staying with us. Hope to see you again. Allah Hafiz.